Moving on to the network architecture that was used for this paper, basically the same network architecture, as I said before, was used for all of the different training periods, and then applying this to all of the different Atari games as well. So there's no change in the overall model structure, and we can see it here in the slide. So first of all, we have a convolutional layer, or several convolutional layers stacked on top of each other, followed then by fully connected layers before you get the output. The output, as we can see, is basically the action that you're supposed to take according to the controls offered by the game. We also have a state up here at the top, which says no input. So that is basically just letting the game progress without any interaction from the model. As input here, we have high dimensional data, namely color video at 60 hertz with the following dimensions. And the only input provided to this network is visual images and knowledge of the number of actions available in each game. So basically it knows also here how many actions you have. However, one key thing to point out here is it does not know what the corresponding effects are of each of these actions. So the model is handed the dynamics of, or is placed inside the dynamics of the game, but it does not know how to navigate up front. There's no information of that. And there's no internal state representation, as we said before. So it only gets the pixels, and then it gets basically, these are the actions you can take, and then it has to figure everything out from there. Taking another step, we can see some performance metrics that were tracked basically during the development progress, or during the training process. The top graphs show the average score per episode for two games, namely Space Invaders and Sequest, and the bottom graphs show the average predicted Q values for the same games. And the figures illustrate that the procedure was able to train a large neural networks using a reinforcement learning signal and stochastic gradient descent in a stable manner. So we can see here from these performance metrics that the average score per episode goes up, which is an indication that the model actually learns to play the game in a more efficient way. And also the average predicted Q value as per the model itself goes up, which is an indication that it learns to predict and find the most the best actions basically in the setting that it's placed in. Looking also at the results for these various games, we have a bit more complicated graph that you can see here. So basically what we have is these bars in here, and they're separated by a blue and a gray region. The blue region indicates the DQN, so basically the primary model that was evaluated. The gray ones are the best linear learners that are currently available, or that were currently available as per this, publishing of this paper. So the higher the bars, obviously the better the model is. And there's a few bars here where the gray bar exceeds the blue one. So here is one example. That is basically where the best linear learner performs better than DQM. For all of the remaining ones, DQM performs better than the learner. It's quite small, but you can also see a percentage down here at the bottom, which indicates the performance of the model compared to the professional human tester. So remember that these were benchmarked against a professional human tester. The score of these models are calculated as 100 times performance of the DQM minus performance of just acting randomly. So as a comparison, because you will attain some value basically if you just act randomly. So there's a random benchmark here, and then that's normalized by the human sort of score, and that is the professional human tester minus the randomized score. And so this is basically what's displayed here in terms of percentage. As we said earlier, 75% of the professional tester score represents the human level. And if we look here, there's a separated line that basically says that everything to the left of this line exceeds 75%. So this is where DQM performs better than, or at least comparable to a human player. And this is below the human level, basically. So we see that that the DQN model outperforms the best reinforcement learning methods on 43 games without any prior knowledge about Atari games used by other approaches. And for the majority of these games, it's also comparable then to human level performance. So that's really something remarkable here. We can also visualize what happens within this model. And in order to do so, a two-dimensional TS&E graph has been plotted here. So that's what we see. TS&E is basically a way to take data in a high dimensional space and then project it onto a lower dimensional space. So because it's very hard to visualize something that's more than three-dimensional at least, TS&E is a good way of sort of clustering things that are related in a higher dimensional space, but in a way that you can actually observe it. So that's what we see here. So basically these regions indicate states that are represented in some way similarly by the model. In addition to just sort of proximity of these, we have some values encoded in terms of the color. So the color here indicates the value function, so the predicted value of the state. And we can see that the highest values are the dark red ones and the lowest values are the dark blue ones. And we can see some different regions in here. Specifically, this TS&E embedding generates similar embeddings for perceptually dissimilar DQN representations with similar expected rewards. Basically, what we mean by this is we have some states here at the bottom right and also at the top here that are not very similar in terms of what they look like. However, in terms of expected reward, they are quite similar. And so that's an interesting clustering that happened basically in this model as a consequence of just, the rewards being similar. So this sort of acts in favor of the fact that the conceptualized sort of clustering that happens inside the model takes into account more than just the visual input as it is, but rather the underlying meaning of that input as well. Also, DQN predicts high values for full and nearly complete screens because completing a screen gives a new screen full of enemy ships. So if we look at the top right here, we see screens that are pretty much full, and down here we see screens that are pretty much empty. And the coloring of these, so based on the gradient here, is dark red. It's a bit hard to see maybe, but it's dark red, these regions, which indicate that the expected value is very high. And that is basically because both of these states are close to being full sets of, just like the ones up here. Because the ones down here, if you just sort of finish off the screen, you will get a new one. And then partially completed screens give less immediate reward and get lower state values. So the encoding here, or the value of the state, is lower than compared to, for example, these ones. So that's what we can see from DQM, and that's it for the very high level overview. And now we're going to dive into the more finer details of how the evaluation procedure and the model works. So stay tuned for that.